Dear engineers, welcome to VEDAGATEACADEMY and welcome to the world of opportunities. Today, the topic digital logic design, and in which logic gates is the basic discussion of today's class. So, the subject is digital logic design, in which the topic logic gates, which is said to be the basic and universal fundamental blocks to design any digital circuits. We have almost around 6 to 7 concepts in this. Let us see one by one in detail. Here, the concept logic gate, the basic definition of this is bilogic device with minimum of more than one input and only one output. I repeat, basic bilogic device with the minimum of more than one input and only one output as the definition of logic gate. According to the definition, I hope you cannot call it as a gate, because not as with the single input, right? So, not with a single input. So, you cannot call not as a gate. So, it is just a basic inverter. We generally use the word not gate, but we should not, because not as with only one input. So, basic inverter. So, the right word suitable for logic gate not is basic inverter. Now, let us see the fundamentals of gates. Gate, symbol, high output with, or when will it get a high output, and low output with, when will it get a low output. And we start one by one. The first fundamental gate, basic inverter, not. And symbol of not is well familiar to you. Here is A and here is Y. And how does not gets a high output? Not gets a high output with low input and low output with high input. The reverse, or you can say inverse. So, high with low, low with high. That's why it is called as basic inverter. And in the sequence, you start with AND. The symbol of AND is exactly half circle. A, B and Y. AND. High output with all high inputs. High output with all high inputs and low output with any low input. And the logic symbol of AND is this, AND. An immediate OR gate. Symbol is this, and the structure is this. A, B, Y, OR gate. And OR will get a high output with any high input. Low with all low inputs. And these are what three called as basic gates, AND, OR, NOT. Basic building blocks to develop any logic circuit. Not as an inverter, it will invert the input given, and it produces a high output only when all the inputs are high, or it produces a high output when any one of the input is high. And you speak about the remaining gates one by one, or high with any high, low with all low. And we have a next gate, not AND. is equal to NAND. It is not AND is equal to NAND. So AND inverter. The symbol AND gate with inverter. Bubble. So A, B and Y. And reverse to AND. High output with any low. Any low input. And low with all high. And consequent, you will have immediate logic as exclusive OR. I just want to rehash once again. So not a simple inverter. And as when A and B both are high, the output is high. Or when A or B, anyone is high, output is high. NAND reverse to AND. So whenever all are high, it is low. And any low, it is high. Reverse to AND gate. And immediate we'll see NOR. Here is NOR. It's what not OR. I'm sorry. Not OR is equal to NOR. Symbol is OR inverter. And structure is OR with inversion. ABY. And high output with it is NOR, right? All low inputs. Reverse to OR. Low with any high. So, high with all low inputs, low with any high input. Now, immediate, we have exclusive OR gate. XR. So, symbol is and the structure is R an exclusive symbol A, B, Y. An exclusive OR responds to get a high output with even parity inputs. Even parity inputs. I'm sorry, exclusive OR high with the odd parity inputs. Odd parity inputs. Low with even parity inputs. And as we all know, parity means number of ones. That means odd number of ones in input and even number of ones in input. Number of ones you call it as parity, so you need to count odd and even. And next one we have exclusive NOR. Inversion to XR. Exclusive NOR. So exclusive OR inverter A, B, Y. High output with even parity inputs. Even parity input. And low with odd parity inputs. Well, so as we already noted, parity means number of ones. So finally, what are the gates, basic and universal and exclusive OR gates in the sequence? Not a simple inverter, low with high and high with low. And when all the inputs are high, output is high. Any one is low, the output is low. Or when any input is high, output is high. All inputs are low, output is low. NAND reverse to AND, high with any low and low with all high. NOR reverse to OR, low with any high and high with all low. Exclusive OR and high with odd parity, odd number of ones in input. So low with even parity. Exclusive NOR, high with even parity. So high with the even number of ones in input and low with odd number of ones in input. Parity counts of number of ones in input. So it can be even or it can be odd. the basic structure of gates, symbols, and input output relations are declared. Input output relations of gates with the truth tables and mathematical equations. So let me explain the same input output relations in the form of binary, because digital logic is always a two valued way and a high and low language. So let us see two input gate and three input gates, different gates and their input output relations. And I'm here with A, yeah, input A, input B, and output AND, output OR, output NAND, output NOR, output exclusive OR, output exclusive NOR. So with two input, AND, OR, NAND, NOR, XOR, XNOR. Let's declare one by one. The inputs are, I'm just taking 0, 1 input. 0, 0, 0, 1, 1, 0, and 1, 1. 0 and 1 as inputs. And the response of the gate, what is AND response? Only when both are high, the output is high. Any one is low, the output is low. And here 0 is low, 1 is high. Hence, low, 0, low, 0, low, 0. Both are 1, the output is 1. Or both are low, the output is low. So, low, any one is high, high, 1, it is 1. So, 1, it is 1. Both are 1, the output is 1. NAND reverse to AND. So, zeros will be 1 and 1 will be 0. NAND output is any input 0, the output is 1. A, B both are 0, output is 1. And, A, B both are 0, output is 1. So, A 0, output is 1. B 0, output is 1. Both are 1, it is reverse, 0. NOR reverse to OR. So, both are low, high. So, any one is 1, so OR is 1, but NOR is 0. Any one is 1, the NOR is 0. Any one is 1, the NOR is 0. Either both are 1, the NOR is 0. An exclusive OR, parity, even and odd I told you. So 0, 0, no ones. So 0, ones. 0 is even number, right? So here I'll say this input consists to EPR, even parity. For even parity, XR is 0. 0, 1, single one. Single one means odd parity, OPR. So for odd parity, XR is 1. 1, 0, single one, odd parity, OPR. So XR is 1. 2 ones, even. So EPR, for even parity, exclusive R is 0. So this is what a parity of the data. And XNOR is reverse. Even parity 1, odd parity is 0. And here are the mathematical relations of the logic gates, what we have. And let me give you, these are the binary relations what we gave. Math relations in the form of A and B. And come back to speak. Not Y is equal to A inversion, single input. And Y is equal to A into B. When both are high, it is high. Or Y is equal to A plus B. Or you can also use OR symbol. And you can just write NOR here itself. Y is equal to A plus B inversion NOR. So you can write NAND here. Not and NAND. Y is equal to AB bar. And we have exclusive OR and exclusive NOR, right? So exclusive OR. So you can observe here 0 1 1 0. Opposite both are 0 1, XR is 1, 1 0 also, XR is 1. So XR is high in these two cases. So how do you write the equation? Both are opposite to each other. Opposite in the sense A inverted B naught plus A not inverted B inverted. A bar B plus AB bar. So this shows opposite inputs. So opposite inputs. Exclusive OR works in opposite inputs. And similarly, and you can make XNR equation as here. Here is 1, here is 1. High for equal inputs. Equal inputs are A bar B bar plus AB. So logic gates, binary relations. Logic gates, math relations between input output. What is not a function equation? Y equal to A bar and A into B. NAND AB bar or A plus B nor A plus B whole bar. XR A bar B plus AB bar opposite inputs. XNOR A bar B bar plus AB equal inputs. And remember AB in the form of binary with zeros and ones. So just highlight once again. So AND is high with when both are high. OR is high with any one is high. Just highlighting high. And NAND is high with any low. NAND is high with any low. So NOR is high with both low. XOR high when opposite inputs are there. XNOR high when equal inputs are there. I hope you're clear with the binary relations of gates along with the math relations, mathematical relations. Now let me show you a 3 input logic structures over here. So A, B, C. Consequent AND, NAND, OR, NOR, exclusive OR and exclusive NOR. Now let me give you the inputs here. 0 0 0, 0 0 1, 0 1 0, 0 1 1, 1 0 0, 1 0 1, 1 1 0 and 1 1 1. So my outputs are AND any input 0 the output is 0, all are 1 the output 1. Only the last case all are 1. All inputs are 1 only in the last case. So here output is 1. Remaining all cases any input 0, output 0 concept is applied for AND logic. Here. Yeah. NAND reverse to AND, right? So 0 will be 1. When all ones it is 0. Reverse to AND. So about OR gate. So any input is 1, output is 1. When all are 0, output is 0. All are 0 only first case. All are 0, output is 0. In remaining all the cases, any one of the input is 1. So output is 1. Yes. NOR. Reverse to OR. Just, all zeros it is 1. And remaining all zeros. If any input is 1, output is 0. Exclusive OR, you need to count parity. So when you look into the parity here, just make a parity here. 3 zeros. So okay, I'll write this side, parity. Three zeros means no ones. No ones is even parity. So EPR. Single one, odd parity, OPR. Single one, odd parity, OPR. Two ones, EPR. single one OPR, two ones EPR, even parity, two ones EPR, even parity, three ones OPR, odd parity. So what is XR? So there are, if they are odd number of ones, 1, even number of ones, 0. So first case even, so 0. Second case, third case odd, so 1. Fourth case even, 0. Then odd, 1. Even odd, so 0, 0. Odd case 1. So where all it is 1, just highlight. So first 1, 2, 4, 7. So 1, 2, 4, 7. The inputs 1, 2, 4, 7, it is high. And XNOR is reverse to it, right? So here, I'm just leaving this column blank, exclusive NOR column. Let me tell you later why. I do not want to fill that column. I'm not interested. I just want to write a comment that I'm just leaving this column. Let me explain in the later stage why didn't I fill this column, exclusive NOR with ABC. Now you are clear with the 2 input relations, 3 input relations, 2 input mathematical equations, and 3 input mathematical equations you are well known, right? So here, and ABC, NAND, ABC bar, or A plus B plus C, NOR A plus B plus C bar. Similarly, we have relations for XOR XNOR also, but XOR XNOR, since we have more number of ones involved, so we have to structure a Boolean function and write the equation, which I will show you in the later stage. 3 input exclusive OR, 3 input exclusive NOR operations. Now, come to speak about the very next topic. Enable and disable inputs of a logic gate. Enable and disable inputs of a logic gate. And if you define the word enable input, and here I just want to go in the other way to explain this concept. First, I'll give you the enable and disable inputs of different gates. By that, would you be able to guess the meaning of enable and disable inputs? Let me try in this way. So now I'm straight away quoting what are the enable inputs, what are the disable inputs for different logic gates. From that, you try to give the definition to me. Yeah. So, gate, enable input, disable input. Yeah. I'm just going to write for different gates. Not, since it is single input, neither enable nor disable. And NAND both. And NAND both. 1 enable, 0 disable. OR and NOR both. 0 enable, 1 disable. And exclusive OR and exclusive NOR, 0 R1 both are enable, no disable. These are how the enable and disable inputs of different logic gates we have. And you already knew the structures and features of logic gates. By that, would you be able to guess the meaning of enable and disable inputs? Yes. And how they will be used. Just try. And just be ready with your reply. And let me extend my topic to explain what are enable and disable inputs. Now, I'm just going to take you another table. It looks easier for you to guess the meaning of enable and disable inputs. Yeah. Here I have input 1. Here I have input 2 and concerned output. So different gates with input 1, input 2, concern output. And my input output combinations are 0, 0, 0, 0, 1, 1, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 0, 1, 0, 1, 1, 1, 0. These are different input output combinations for different gates, not of one together. But in all these cases, I can claim first input, input 1, is called as enable input. I am giving you a second hint to guess the meaning. I am giving you a second hint to guess the meaning. Here one hint by the table and here a common universal hint. In all these cases, first input is called as enable input. Why? And what is the meaning of enable input and disable inputs? Just look out once. May any hint for you to guess the meaning of enable input? It is not that enable input, the one to enable the gate, disable input, the one to disable the gate. Simply where logic 1 is enable, logic 0 is disable. And it is definitely not so simple as you guess. And even if you observe these tables, you will understand it is just not simple so. It has some logic, meaning. The subject itself is logic design. And of course, this topic is logic gates. So everywhere some logic will be involved. If you guess that logic, it will be just a cakewalk. And you'll play a game to answer the questions. Yes. Can we just try to get the hints? Yeah. You see this? And just like an aptitude test to guess what logic is in the table. First two cases, input to 0, output 0. Input to 1, output is 1. Second two cases also input to 0, output to 0. Input to 1, output is 1. So can I say in these four cases, output is input 2. Here, input to 0, output is 1. Input to 1, output is 0. Input to 0, output is 1. Input to 1, output is 0. Can I say it is reverse? Input to overbar? Yes, it is. Now, output is the impression of input 2, either as same or inverse. I repeat, output is the impression of input 2, either as same or inverse. But why input 1 is called as enable input? Because input 1 is the reason for that. Because of this 0, it is passing a 0 as 0 or 1 as 1. If one input is 0, second one 0 means 0, 1 means 1. Is it not OR gate? Yes. If one of the input is 0, other one 0 means 0, 1 means 1, OR gate. So, who is making this to pass? This one. Because this is 0, second input is passing. Similarly, if one of the input is 1, second one is passing as it is. Both are 1, the 1, any 0 is 0. Is it not AND gate? Yes. And if one of the input is 0, second one is coming in reverse way. 0 means 1, 1 means 0. If any one is 1, 0, both are 0, 1. Is it not NOR gate? And last one, and because of this one, it is coming in a reverse way. So, any 0 output is 1, both are 1, output is 0. NAND gate. So, input 1 is enabling input 2 to come to the output. And I just wish to show this in mathematical equations in a better way. Can I? Yeah, I will. AND gate. Y is equal to AB. Can I say Y is equal to B when A equal to 0? Sorry, A equal to 1? Yes, it is. When A is 1, Y is B. 1 into B equal to B. Now, who is the reason for B coming to the output? I repeat. Who is the reason for B coming to the output? A, right? No, it is not A. It is 1 on A. So, 1 on A making B passing to the output. Similarly, NAND. What is the equation? Y is equal to AB bar. So who is the reason for making B bar coming to the output? Can I say Y is equal to B bar when A is equal to 1? Substitute A is equal to 1. So 1 into B bar equal to B bar. So who is making B bar to come to the output? 1 and A. It is not A, it is 1 and A. Clear with this, right? So hence, both these cases, this 1 is called as enable input. In which of the cases? And NAND and 1. NAND also 1. 1 is enable input. Similarly, let me take OR and NOR. OR expression. Y is equal to A plus B. Can I say Y is equal to B when A is equal to 0? Yes, 0 plus B is B. So 0 on A making B coming to the output. Similarly, NOR. Can I say Y is equal to A plus B bar? NOR expression. Can I say Y is equal to say B bar when A is equal to 0? Yes. In both these cases, so 0 is enable input. Observe in the case of R and NOR. R and NOR here, R 0, NOR also 0. So if it is 0, then second is passing. B as it is B or B bar as it is B bar. And if you look into the next structure, exclusive R. Why it doesn't have enable input? Anyhow, let me define enable input overall here. Enable input definition. Enable input the one to enable the gate to respond by other inputs. I repeat, to respond by other inputs. The simple definition. So 1 and A making B passing. So 1 and A making B bar passing. So like how? So this 1 is the reason for making B coming to the output. Or here 0 the reason for making B coming to the output. So it enables the gate to respond by others. Or it enables other inputs to respond on the output, but not on its own. So that is what the definition of enable input, which is structured in all these cases. Now, if I just give you a simple definition of disable input. Yeah, I'm just here to explain the meaning of disable input along with the examples. Disable input is maybe you'll be able to guess on your own. Input 1. Input 2, consent output. Yeah. Come to speak about that. If any input is 0, I am not bothered about second output is 0. And if any input is 1, I am not bothered about second output is 1. And if any input is 0, I am not bothered about it, output is 1. If any input is 1, I am not bothered, output is 0. So if any input is 0, output is 0. And if any input is 1, output is 1. And if any input is 0, output is 1. And if any input is 1, output is 0. Reverse. So here, second one has become irrespective. So you can just straight away, understand the logic here. If it is 0, it is 0. If it is 1, it is 1. If it is 0, it is 1. If it is 1, it is 0. So who is the reason of making the output decision? Of course, input 1, but definitely not input 2. So of course, input 1. So disable input. In all these cases, input 1 is called as disable input. Definition: disables the gate not to respond for others. I repeat, disables the gate not to respond for others. So blindly, if any input is 0, output is 0. It is AND, logic AND. If any input is 0, output is 0. And logic OR, if any input is 1, the output is 1. Logic NAND, if any one is 0, output is 1. Logic NOR, if any one is 1, output is 0. Decision maker is input 1 itself, but not input 2. It disables the gate not to respond for others. It disables the all other inputs not to come to the output. I can say that. Can I say independent and highest prior input to control the gate? Yes, we can say that. Independent and highest prior input to control the gate is disable input. If that is decided, output is decided by not working on the others. So now finally, what is the necessity of introducing enable and disable inputs? Can I just state that? Enable and disable inputs, E input and D input, are introduced to control the gate. So whenever you are controlling the gate, it is as well as controlling the circuit. When you are controlling the circuit, it is as if you are controlling the application. As and how user wants. So tell me this. Enable and disable input are introduced to control the gate in terms the circuit, in terms the application, as and how the user wants. So to take control of logic gate, logic circuit, logic application, we have taken enable and disable inputs. So if enable input is coming to the picture, it is allowing others to come to the output. If disable input is coming to the picture, it is not allowing others to come to the output. That's how the distinction is made between them. Good. So switch and bulb equivalent circuits of logic gates. Each and every logic gate, let us represent with the switch and bulb equivalents. So switch as an input, bulb as an output. Let us represent different logic gates we have. First I am taking NOT. What is the NOT relation? Inversion, right? Study this. So try to study this circuit. Here is voltage source and here is resistor, here is switch, here is bulb. So what is the relation between switch and bulb now? In this circuit, if switch is closed, power goes through the switch, bulb will be off. If switch is open, it has to go through the bulb. So reverse. Switch closed, bulb off. Switch open, bulb on. Can I say the relation between switch and bulb? Yes and B. Switch is on, bulb is off. Switch is off, bulb is on. Finally, inversion relation between switch and bulb. Hope you're clear. Now, let us speak next about AND operation. Switch 1, switch 2 and bulb. Switch 1, switch 2 and bulb. I'm just taking two input. Switch 1 is on. Sorry. Switch 1 is off. I don't bother about this, it is off. Are the switch 2 off also? It is off. Only when both are on, it is on. Bulb is on only when both switches are on. Can I just draw the circuit like this? Series the switches, bulb also followed by current limiting resistor, voltage source. So, V are switch 1, switch 2, bulb. So, only when these two are closed, the bulb will be on. If any one is off, power will not go. It will, it has broken, right? It has a break for the power to go, right? So, series in switches and the gates AND operation. And similarly, R, A, B and bulb represent the OR operation. A is on, bulb is on. Whether B is on, the bulb is on, or both are on. Only when both are off, bulb is off. You know well, right? OR gate. It is getting a high output with any high in. Whether A is on, the bulb is on, B is on, the bulb is on, both are off, the bulb is off. Draw the circuit. And I hope it is a parallel combination. Parallel switches indicates OR operation. Correct? So, switch 1, switch 2 are voltage source and bulb. How does the bulb glows? It can be either this or it can be either this. Current can flow either this way or in this way to glow the bulb. When both are off, of course it is off. It won't be glowing. So, NOT relation, AND relation, OR relation. Now, NAND and NOR. So, as you know well, relation of NAND. You can see that. Switch 1, switch 2 and bulb. So, any input is 0, output is 1. So, switch 1 is off, bulb is on. Switch 2 is off, bulb is on. When both are on, bulb is off. Right? If any switch is off, the bulb must be on. If any switch is off, the bulb must be on. So, now draw the circuit. Break. Try to guess the logic here. Switch 1, switch 2, bulb, R and V. So, if there is a break for S1, bulb glows. Break for S2, bulb glows. Break for both, bulb glows. But when both are on, the power will be bypassed. Bulb will not glow. I hope you are clear. If any switch is off, it will go through the bulb. If both are on, the power will bypass, the bulb will not glow. The relation of NAND. And speak about the last one. Sorry, out of universal. NOR. Right? So, it is reverse to that, right? Can I say straight away draw the circuit? Can you guess the input-output relations here? Do they resemble NOR? Yes, try to guess. So if anyone is on, the power will be bypassing. It will not glow. Only when both are off, it will glow. No relation. If any input is 1, the output is 0. If both are 0, the output is 1. No relation. If any switch is off, the bulb will glow. Right? If both are on, so it will not glow. So that is how the way it comes to speak about that. Either this is on or this is on or this is on. So if any one is on, it will bypass. It will not, glow. If both are off, of course it will glow. That is how the NOR relation which works on. I repeat again. If any one is on, the power will be bypassing. If both are off, the power will go through the NOR relation. And how would you define? Switch and bulb relations of NOR here are switch 1, switch 2 and bulb. NOR relations. Switch 1 is on, bulb is off. Either switch 2 is on, still the bulb is off. When both are off, then only bulb is on. That is how we design here. You could observe. And here all are in parallel, right? Switch 1 is on, the power bypasses. Switch 2 on, power bypasses. Both are on, the power bypasses. Only when both are off, the power goes like this and the bulb will glow. That is how the relation of NOR. Now comes into the picture exclusive OR. And of course inversion exclusive NOR. The equation of exclusive OR, as you all know well, A bar B plus AB bar. So if you work into this in the form of switches, when both the switches in opposite form, when both the inputs are in opposite form, the bulb will glow. So I can say switch 1 not equal to switch 2. So bulb is on. Switch 1 equivalent to switch 2, bulb is off. Now let me use single pole double through switches as a combination using SPDT switches, single pole double through combination of switches. We will be able to design this logic. So switch 1, switch 2. Here the meaning of SPDT is thus. So you can either operate switch in that way or this way. SPDT. S1, S2. Yeah. Come back to. You can either operate in this way or in this way. You can either operate in this way or in this way. You can design the switch as contact of this side when the switch position is high and contact of this side when the situation is low. Similarly, low and high. Or you can say on off. So when it is on, contact this side. When it is off, contact this side. When it is off, contact that side. When it is on, the contact this side. Why don't you join high and low? Similarly, low and high. And just keep a current limiting. Voltage source. Bulb here. Now you could observe S1 high, S2 low completed. And S1 low, S2 high. Then also completed. Keep S1 high and S2 high both this way. No, it wouldn't be. Here is a break. And similarly, you just keep low and low and break. So high and low contact completed. Low and high contact completed. Opposite cases the contact is completed. So equal cases the contact is not completed. When you work out this, and you need to remember the switches what we designed for staircases working. and we have a 2-3 storied building, and we have bulbs on the steps to go. And as you know well, we can operate the bulb of first floor either from ground or first. Bulb of second can be operated either from first or second. Like how you can have two different switches to operate in one device. If that is on, this should be off. If this is on, that should be off. Either even a fan working with you in the room can be having a switch at the bed and switch at the main board. You can use that switch or this switch to switch on the device. If this is on, that should be off. If that is on, this should be off. Opposite way, working with the switches is what called as exclusive OR logic. So mostly involved in staircases design, staircase switches design and working on. If you go with exclusive NOR, it is simply reverse to that. As you can just guess the logic to go. So fine, all these are very important for you and a competitive requirement to understand. By looking into the diagram, you must be able to guess immediately what logic it has. If switches in series along with the bulb, it is AND logic. If switch in series with the parallel, if bulb is in series with the parallel switches, it is OR logic. And bulb and switch on both parallel to each other, and that's what not logic. And if you could see this, series switches bulb in parallel, NAND logic. All are parallel and switches and bulb, that will show you a NOR logic. So single pole double through, contacting in opposite way, and this comes you with XOR logic. So like how by the diagram given or by the circuit given, and you must be able to guess the logic involved in that. Simplest one. And very immediate topic. Let us speak about better universal gate. Who are the universal gates? What are the universal gates and why are they universal gates? As you all know well, NAND and NOR are said to be the universal gates because any logic circuit can be developed either by only NANDs, or by only NORs. Hence they are called as with the combination of only NANDs or with the combination of only NORs, and you will be able to develop any logic circuit. Hence they are called as universal gates. Now from these universal gates NAND and NOR, can you tell me which universal gate is better in what way and why? If I ask you a question, which universal gate is better, people will obviously respond NAND from anywhere. But I have questions to you. Which universal gate is better in what way and why? And I just want the bit of analysis here to conclude which universal gate is better. Let us see what is that analysis to conclude whether NAND or NOR the better choice for developing the circuits. Yeah. Here I have the parameter size and weight. In the terms of size and weight, which gate is better? And I have the parameters cost and complexity. And I have the parameter speed. And I do have a parameter number of gates required to develop others. Number of gates required to develop other gates. Size and weight, cost and complexity, speed of the operation, number of gates required to develop others. And when I raise these questions, funny, in one classroom, one student of your engineering community has given a very funny reply. When I ask you in size and weight who is better in NAND and NOR, he has just given a simple answer that, sir, I never put this in a weighing machine and checked out what is the weight of NAND and NOR. Surprising. When I asked you cost and complexity, he said, sir, I did not buy any time in the market to know the cost and complexity. Immediately when I said a speed, and he said, I did not travel on that. Thank God. And a funny replies. Come back to the originality. These parameters, size and weight, cost and complexity, speed of operation, And these three are not the ones to compare NAND and NOR, it seems. You cannot compare whether NAND is better or NOR is better by these parameters, because these parameters are decided by logic family behind the gate. ECL, DTL, TTL, CMOS, the logic family. If I mention logic family, then we can say which is better in size and weight, which is better in cost and complexity, which is better in speed of the operation. So, logic family decides that. Now come back to speak. Number of gates required to develop other gates, whether NAND is better or NOR is better. So guess, and many will say NAND, and some cases NOR. The originality, both will play same role or different role, you guess. Same role or different role? Obviously different role, would not be the same role. Anyhow, both will play neither same role nor different role, their own role. I repeat, in some cases if NAND is better, in some other cases NOR is better. In one circuit if NAND takes lesser, in the other circuit NOR takes lesser. Like how we can conclude, until and unless you declare the circuit whether NAND is better or NOR is better. Anyhow, all these parameters have become, not the reasons for explaining whether NAND and NOR is better. The one and only the important parameter to just conclude whether NAND or NOR is better is ultimately power consumption. In the view of power consumption, we can declare which is better choice in NAND and NOR. Now let me tell you the explanation. Let me explain you what way whether NAND and NOR comparing with power consumption. When I have A and I have B, and I'm just getting with NAND operation. And here, and if A is low, output is high. Even if B is low, the output is high. Even if both are low, the output is high. The other case, fourth case, when both are high, output is low. And this is our NAND gate operation, right? So any input is low, the output is high, both are high, the output is low. I'm here taking high in the main choice and concluding that it is getting 3 cases high output, 3 by 4 cases high output. Only one case it is getting low output. In digital circuits, if sum of products is a default equation, SOP function, if I say 1 is my default requirement, so 3 by 4 cases getting high output, even with 1 low or all low inputs. Please conclude. 3 by 4 cases, NAND is getting a high output even with 1 low or all low inputs. Even if 1 low or all low, it is getting high output. So, whereas NOR, we can just conclude that A, B, NOR operation. And just tell me the input output relations. A high, it is low. Can I say low as a not high? Yeah, why not? Any high input, low output. Low is not high anyhow. So even if B is high, it is not high. Even if both are high, it is not high. Not high means low. Only when both are low, it is getting a high output. Now, same comparison let us take in the different way here. 3 by 4 cases, it is not getting high. Getting low or not getting high, both are same. But here we are highlighting not getting high as a requirement. Not getting high even with 1 high or all high cases. 1 high or all high cases. Now tell me which is better. Even after spending low power either on 1 or all, it is getting high. Even after spending high power either on 1 or all, it is not getting high. So, getting high with even low power, not getting high with an high power. So, we wish always to highlight NAND is a better choice for logic operations in designing the circuits. So, in the view of power consumption, neither in the terms of size, weight, cost, complexity, speed of operation, those all are decided by logic families behind that, like ECL, DTL, TTL, CMOS, whereas power consumption, the finest parameter, decides the involvement of logic NAND as a main gate developing the logic circuits. And immediate after this, we have to prove NAND and NOR as universal gates by designing all other gates only by NAND gate or only by NOR gate. Let's look into that. Proving NAND as universal gate by designing all other gates using only NAND and only NOR. Yeah. I'm here with starting. I just want to design NOT as a first basic. NOT by NAND. So what is the NOT equation? As we all know well, A bar. From where we want? NAND expression, AB bar. Can I say A into A bar is equal to A bar? Yeah, exactly. Can I even say A into 1 bar is also equal to A bar? Exactly. So both the ways you can develop NAND is NOT. But can you guess which is a better choice out of them? Yes. If I take power consumption into the picture, using A into 1 bar, 1 means VCC, always supplying VCC will have more consumption of the power. Using both the inputs will comparatively have less consumption of power. So let me ultimately prepare A into A bar as the preference. So this is my first preference. So I can develop NOT in this way, joining both. A into A bar is equal to A bar. I can also develop NAND as NOT in this way. A here, VCC here, referred as 1. So here is A into 1 bar is equal to A bar. Now I have a question, and we've already concluded that. So this is what the better choice than this, because VCC is always supplied. But in one case of digital circuit, designing a special digital circuit, sequential digital circuit, we forcefully implement this method of using. Of course, when the application demands, we don't have any option except this. So guess where is that? In which sequential circuit design, we use this logic of NAND implementation as a part of it. Just recollect which sequential circuit we use this logic to design the circuit. Even after power consumption is high, we prefer that. Keep thinking. When the time comes in discussion of sequential digital circuits, I'll raise this point once again. Yeah. Now let me come back to explain. After NOT by NAND and then OR by NAND and by NAND. So as we all know well, AND operation is AB. From NAND operation is AB bar. So how do you get AB from AB bar? Can I say AB double inversion is equal to AB? Exactly. So first NAND, connective one more NAND, but this is inverter. A, B, AB bar, AB double bar as AB. So two NANDs are involved in designing AND gate, right? AB. And let me speak about OR logic from NAND. OR from NAND. Well, come to speak about A plus B from AB whole bar. Just look into this. So AB whole bar distribution is equal to A bar plus B bar. But I want A plus B from that. Can I implement in this way? To remove over bar, can I place another inverter? both the sides LHS and RHS over A bar into B bar whole bar is A bar bar plus B bar bar is equal to A plus B. Now the circuit to design is, and this is what your main NAND. So A inversion A bar, B inversion B bar. So here the inputs are A, B, A bar, B bar, A plus B. Now look into these realizations. How many NANDs are used in developing not single? How many NANDs are used in developing N2? How many NANDs are used in developing R3? And immediately let us look into the developments of exclusive OR and exclusive NOR. Anyhow, when R is ready, inversion, why don't you think about that? Yeah, R inverter, keeping one more NAND here, A plus B bar. So that is what? NOR by NAND. How many gates are used? 4. So 3 gates, we got OR operation. 4 gates, we got NOR operation. Immediate to this, let us see the developments of exclusive OR and exclusive NOR. Exclusive OR by NAND. It has lot of importance in dealing with circuits, competitive examinations, industrial requirements, and analysis of logic evolutions. Now let me explain. Exclusive OR gate developing by NAND and NOR. NAND first. XR and XNOR by NAND. Exclusive OR and exclusive NOR by NAND. You have exclusive OR in the sense A bar B plus AB bar, right? A bar B plus AB bar. Now we have to develop this equation using NAND operations. So I have to go as, so A bar B from AB bar, also AB bar also from AB bar. So you know the expression of AB bar expansion, A bar plus B bar, and here also AB bar expansion, A bar plus B bar. But I want A bar B, AB bar from this. Now just see how will we get that? Multiplying this one with what term I will be getting A bar B? Can I say B? Yes. B into A bar plus B bar. What is the answer? BA bar, this term. So BB bar is cancelled. BB bar is cancelled. Multiplying this one with what term I will be getting second term? So can I say multiplying with A? Yes. A bar cancelled, AB bar is left. So this is what NAND AB bar. It is what A bar plus B bar. Multiply this with B and you got first term. Multiply with A, second term. Now finally, can I say this? A into A bar plus B bar is again AB bar, no? Plus B into A bar plus B bar is AB bar, no? Simple. But I don't want a plus in between. I want completely in the form of NAND. One NAND has anyhow appeared. So let me give you the complete NAND analysis. So it is A into AB bar into B into AB bar. Let it be plus, in the next step I will make it into. So if you apply double inversion, the operation, the value of the function will not be changed, but plus becomes into, right? Into becomes plus, right? As you all know well. So applying double inversion will not change anything. You can keep a bracket here. It seems to be A plus B whole bar. It could be of A bar into B bar, isn't it? Now, so to make this plus as multiplication into, to get into the complete NAND form, I have applied you double inversion. Keep the first inversion as it is. Keep the inner inversion converted according to De Morgan theorem. Finally, A into AB bar into B into AB bar finally over bar. And this bar will remain as it is, right? And this is how the exclusive are evaluated from the NAND operation. Now here all are NAND gates. And guess how many NANDs are there? How many NANDs are there in this? Yeah, let's just calculate. Here is one. A into AB bar 2. B into AB bar 3. And the upper one 4. The number of NANDs involved here are 1, 2, 3 and fourth one. This is 4. So using 4 NAND gates I can develop this equation. So let me draw the circuit. Yeah. What is the output of this? A exclusive RB. What is this input? A into AB bar. What is this input? B into AB bar. And how do you get those things? AB bar is common anyhow for both. Multiplying that with A, multiplying that with B. Multiply with A, multiply with B. AB is however common. So, A and B. And this is AB bar. A into AB bar, B into AB bar, Mottaniki, total overall A exclusive RB, sorry. So, inversion to that, A X nor B, inversion to this. So, here you get A X nor B. So, XR and XNOR both are ready. Using 4 gates we got XR operation. Using 5 gates we got XNOR operation. And let me tell you the opposite way, the other way to develop XR. So, I'll just go in this way. And this is first model. Second model is XNOR and XR. I'm sorry. First XNOR, then inversion to this XR. We can also do this. XNOR and XR. And here XR and XNOR. But I'm taking now XNOR and XR. Let's see how do we do that. By NAND. So, XNOR is A bar B bar plus AB. I can just do this as A plus B whole bar plus AB. I can do this as just make a double inversion. A plus B whole bar plus AB, double inversion. Yes. What is the impact of double inversion? Please tell me. This bar will be cancelled, plus will be into, and AB will get bar again. So, the resultant output will be A plus B into AB bar whole bar. Because I am taking this first logic in brackets. Yeah. Treat this as completely A. Treat this as B. A plus B whole bar equal to A bar into B bar. So, bar cancelled and AB gets a bar. Upper bar remains the same. And now, we knew how to get this from NAND. And this is already NAND. So, here you will get A plus B by NAND already we developed previously. And upper again a bar. How many NANDs are involved here? To get A plus B, 3 NANDs. And AB bar is 1 NAND. And here is 1 again. So, 3 plus 1 plus 1. How many? Totally 5 NANDs have been shown here. 5 NANDs. Let's see the circuit. Circuit of this. Yeah. First A plus B. A into A bar, B into B bar together NAND operation. Then one more AB bar. Together NAND again. And this is circuit. inputs A here, A bar, B here, B bar, AB, AB bar. So this would be A plus B. So A plus B, AB bar, NAND again. So here what you get? XNOR B, A XNOR B. Inversion of this. A exclusive RB. So how many gates to get XNOR? 4. How many gates to get XR? 5. Upper. How many for XR? 4. XNOR 5. 4 XR, 5 XNOR. 4 XNOR, 5 XR. Two different ways of getting exclusive operation by NAND gates. Now let me tell you, out of this, which is a better choice in working out. I'm just going to name the equations as if let it be y1, let it be y2, let it be y3, and let it be y4. And we got y1, y2, y3, y4. Yeah. Y function gates. Y function and gates. Yeah. Tell me that if y is y1, what function is derived? Here. A exclusive RB. So A exclusive RB. How many gates? 4. And if y is y2, what function? A exclusive NOR B. How many gates? 5. If y is y3, and here 4 again I feel, 4 XNOR, sorry 4 gates to get XNOR operation. So it is A XNOR B, so 5 gates again. So if y is y4, it is XOR operation, 6 gates are used. Now tell me, exclusive OR by 4 gates and exclusive OR by 6 gates. XOR by 4, XOR by 6, which is a better choice? Ultimately, y1 XOR by 4. For XOR, this is better choice. But for XNOR, you could observe y2 also 5, y3 also 5. So y1 is better choice for XNOR. So choose y1 for simple exclusive OR by 4 NANDs. Most important multiple choice requirement. Choose y1 for simple exclusive OR by 4 NANDs. Then what about XNOR? Both are there similar. So when they are similar, let us compare the other parameters. What are the other parameters? Between y2 and between y3, when gates are same, and I want to compare power consumption and speed of operation. I repeat, and I want to compare power consumption and speed of operation. Now tell me one thing, does power consumption varies on number of inputs or number of times power taken from inputs? I repeat the statement. Does power consumption varies from number of inputs or number of times power taken from inputs? I hope it is number of times power taken from inputs but not number of inputs. Power consumption. Similarly, speed of operation doesn't varies by number of gates, it varies by number of levels. Will you agree? Yeah, you have to. Speed of operation will not vary by number of gates, it varies by number of levels. And let us count those things here. Firstly, power consumption. To get to y2, yeah, here is y2. A twice used, B twice used. See here, initial level. Power consumption will be depending on the initial level inputs to go. Twice A, twice B. And similarly, to get y3, 1, 2, 3 times A, 1, 2, 3 times B. You could understand. All of you, please carefully concentrate here. Yeah, here 2 inputs joined, right? 1, 2, again 1, 3. 1, 2, again 1, 3. So 2 times A, 2 times B, 3 times A, 3 times B. Ultimately, power consumption less here, more here. So y2 is of less consumption of the power. y3 is of more consumption of the power. So, if you want a low power exclusive OR, choose y2. If you want a faster exclusive OR, choose y3. That is how the deviation is. And speed of operation. And let us draw the levels when you work out with the speed of operation. The levels can be drawn here as here is level 1. Here is level 2. Here is level 3. And this is anyhow level 4. In this diagram, the levels are, this complete one is level 1, and this is level 2, and this is level 3, L1, L2, L3, L1, L2, L3. Now see how many gates are involved for Y2. Y2 is here. First level, second level, third level, fourth level, I think you got Y2. So 4 levels. It seems it is 4 gate delay. 1, 2, 3, 4. But generally 5 gates are involved, but these both will be working at a time. So only 1, 2, 3, 4 levels. So level 1, level 2, level 3, level 4. So 4 gate delay. So next here observe. L1, L2, L3. 1, 2, 3, 4 levels, 4 gate delay. 1, 2, 3, 3 levels, only 3 gate delay. Even if 5 gates are same here, but these 3 will be working at a time. Try to observe. All these 3 are working at a time. All these 3 are working at a time. So 1, 2, 3 levels. 1, 2, 3, 4 levels. So speed of operation, if it is 4 levels, ultimately the speed is lesser. Only 3 levels, speed is more. So if you want a faster operation, Y3, and power consumption, if it is less power operation, Y2. So whenever you speak about power consumption, use this, and whenever you speak speed of operation, use this. I hope this analysis is very important for competitive requirements, industrial requirements, interview perspectives to work on. In academics, you might remember we don't be using these two types of explanations. We'll be taking only a standard explanation, that to the very first one. Second one, comparisons, all those we won't be taking. That is why competitive is always concluded as, it is analysis always. It gets you the best analysis to give you the nice one. Let me explain the next case, proving NOR as universal gate. Proving NOR as universal gate. Here, let us implement the same operations again using by NOR gate to prove NOR as a universal gate. Now come to speak about the first one. Not by NOR. Not as again inverter. From NOR operation A plus B bar. Here, can I say A plus 0 bar is equal to A bar? Can I also say A plus A bar is equal to A bar? Exactly. A plus 0 bar equal to A bar or A plus A bar equal to A bar? Both we can see, but can you tell me the better choice? Of course, using 0 will consume less power than using both of them, right? So this is a preferable choice than A plus A equal to A bar. But in general, joining both of them as A plus A bar equal to A bar is used until and unless the power consumption comes into the picture as a priority. So in common we use this one only, A plus A bar equal to A bar. Now let me draw the diagrams. 0 is ground. So this is A bar. As usual, joining both. And here also you get A bar. So as I told you, the preferable circuit is the first one. And next, let us see OR by NOR. OR is what? A plus B. From NOR is what? A plus B whole bar. Can I say A plus B whole bar, A plus B double bar equal to A plus B. So, draw the circuit. Yeah. Is it this? AB? A plus B bar and A plus B. How many gates are used? 2. How many for inverter? 1. And let me see how many gates are used for AND operation. AND by NOR. AND is what? AB. From NOR is A plus B bar. You speak about A plus B bar expansion, A bar into B bar. But I want AB from this. Can I say inverters, LHS and RHS both the sides? Yes, it is A into B. So A bar plus B bar whole bar is A bar bar into B bar bar is equal to AB. Draw the diagram. Here is NOR. Inversion to A, inversion to B. Joining both and joining both. A here, B here. A bar, B bar and AB. How many gates are used? 3. How many for NOT? 1. How many for R? 2. How many for N? 3. Let me see the most important point again, exclusive R and exclusive NOR operation. I just wish to begin XNOR and XR. It can be any form, right? XR and XNOR, XNOR and XR can be any way to go. And as you all know well, exclusive NOR is A plus, sorry, A bar B bar plus AB from NOR A plus B bar. So can I say I'm sorry, A bar B bar plus AB. Yeah, A XNOR B. So A bar plus B into A plus B bar. What is this expansion? Yes. So A bar A cancel, A bar B bar. B A left and B bar B bar. B bar B B bar cancel. So A bar A cancel. So A bar B bar is left. So B bar B cancelled, B A is left. And this is how you get an expansion of A bar B bar plus AB. But I want this from NOR and this from NOR. Both from NOR only. So this from NOR is A plus B bar, right? And this also I want from NOR only. So NOR expansion can I say? Here also can I say? Now the very immediate step is, how do you get A bar, I'm sorry, yeah, A bar plus B from A bar B bar? How do you get A plus B bar from A bar B bar? So A plus B bar expansion. Can I say A plus of A bar into B bar? What is the output? A bar is cancelled, so A B bar is left. Sorry, A plus A bar is cancelled, A plus B bar is left, second term. So similarly, B plus of A bar into B bar. Using this A bar into B bar, I have to get this A bar plus B. Similarly, using this A bar into B bar, I have to get A plus B bar. The option is doing plus. So A plus of A bar into B bar, B plus of A bar into B bar. A plus A bar cancel, A plus B bar is left, second term. B plus A bar left over, first term, B plus B bar cancel. So next, again get back, A plus of A plus B bar into B plus of A plus B bar. So adding A to A plus B bar, adding B to A plus B bar. That is how. Previously in the case of NAND, multiplying AB bar with A, multiplying AB bar with B. And here adding A to A plus B bar, adding B to A plus B bar. Simple, but I don't want multiplication here, nor in the sense I want plus. To get into plus or plus into, over bar is the solution. But single over bar is again a confusion. Double over bar will not have any effect. So let me keep a double over bar. So A plus of A plus B bar into B plus of A plus B bar, double inversion which will not have any impact on inverter, another inverter. Keep this first inverter here. Now tell me the output. A into B whole bar, nothing but A plus B whole bar. So expansion is A plus of A plus B bar into becomes plus B plus of A plus B bar, the upper bar remains the same. So how many NORs are here? How many NORs are here? A plus B bar is 1, A plus B bar is 1, B plus A plus B bar is 1, totally 4 like previous say. So let us draw this on the top. It may be congested over here. Let's do that. Yeah, the equation is A plus B bar plus B plus A plus B bar, 2 bars, right? One more inverter. Yeah, inner bar is cancelled, upper bar is done. Now how many NORs are there? I'm sorry. Here is bar, here is another bar, upon this over bar. How many NORs are here? This is 1, 2, 3, 4. 1, 2, 3, and this is 4. 4 NOR gates are used here. So let me draw the circuit. Same like previous, how did we draw with NAND? Yeah, notations. A, B, A plus B bar. And here is A plus B bar. And here is B plus A plus B bar. And overall AX NOR B. AX NOR B inversion. A XOR B. So this is first method as we have done in the NAND case previously. Second method, XOR and XNOR. By NOR. XOR and XNOR by NOR. XOR is A bar B plus AB bar. From NOR is A plus B bar. A plus B into A bar plus B bar. A bar cancel, AB bar, B bar cancel, B A bar. It can be expanded like this. Further, A plus B into AB whole bar. Further, I just don't want into here, plus, because it is NOR operation. A plus B into AB bar, double inversion. Yeah. Double inversion. Expansion is equal to A plus B will get bar. AB bar will be cancelled. It will be AB over bar. Now how many NORs? Yeah. To get AB, 3 NORs. A plus B bar is 1 only, and this is 1 again. So totally 5 NOR operations to get on. Circuit let us draw over there. Yeah. Now come back to speak. Oh, NOR, right? Here is NOR. Another NOR to get AB operation. For that, A plus B bar combination. Yeah, 5 NORs here. A, B, A, B. A plus B bar. A, B. A exclusive RB. A exclusive NOR B. So 6 gate circuit developed. Now let us draw Y1, Y2, Y3, Y4 as like previous to compare which is better. Yeah. Y1, Y2, Y3, Y4. Now compare Y1, Y2, Y3, Y4. So Y function gates. Y1 is exclusive NOR. Observe here, exclusive NOR. Y2 is exclusive R. Y3 is again exclusive R. Y4 is exclusive NOR. Number of gates. So 1, 2, 3, 4. To get Y1, 4 gates. Y2, 4 plus 1, 5 gates. Y3 on the top, again 5, 1, 2, 3, 4, 5. Y4, 6 gates. Now tell me one thing, XNOR by 4, XNOR by 6, which is better? XNOR by 4, XNOR by 6. Ultimately, Y1 is better for XNOR. And for XR, both are having same stories, 5 gates, 5 gates. So whether this diagram or that diagram to develop XR, 5 gates have been taken. Now ultimate choices, power consumption and speed of operation as we declared previously. Story is same again. So between Y2 and Y3 comparisons, twice A, twice B, thrice A, thrice B. Same story like the previous case. A twice used, B twice used. A 1, 2, 3 times used, B 1, 2, 3 times used. Try to observe here. A twice, again A, 3 times. B twice, again here, 3 times. So consumption is ultimately more here, less here. Y3, more consumption. Y2, less consumption. Speed of operation, as already we have drawn the levels, you remember. Level 1, level 2, level 3, level 4. Whereas here, level 1, level 2, finally level 3. So L1, L2, L3. 3 levels and 4 levels. So Y2 is of 4 levels. So it is less speed. Y3 is of more speed. Our preferability finally. So less power, this is preferred. Faster, this is preferred. And you cannot get a combination of low power and faster together because both are in opposite forms. And this is how NAND and NOR are used to develop all other gates, which is the most important parameter used in arithmetic circuits, developments, competitive, industrial requirements, interview questions. And this topic has a vital role in understanding. But remember one thing, whenever you draw these circuits, just don't remember blindly by practicing the diagrams. Always remember to go with the math analyzation like this. So how do you develop XNOR and XR by NOR? So XNOR equation is this, A bar B bar plus AB from NOR. So slowly you have to derive getting this operation XNOR from NOR equation. Like how? XOR from NOR equation, like that. You need to always think mathematical behind to go, simplest way to understand. I don't wish you to by heart all these diagrams. Remember, please don't do that. It is dangerous. Sometimes you may make a mistake. Sometimes you may forget and you'll stuck up. All these things may happen. Better ways, always go with the math analysis. Even if it is time taken once and twice practice and do the best. And immediate after this, how many gates are taken in comparison in overall? Let's see. A short question. Number of Nands and NORs. For all other gates. Oh, let me draw this like a table. Gate minimum NANDs required, NORs required. To develop NOT and or NAND, NOR, exclusive OR and exclusive NOR. To develop these gates, how many gates are required one by one? Not sir, how many? One. So, not by NAND 1, AND by NAND 2, OR by NAND 3, NAND by NAND. So, if AND are taken 2 gates and ultimately NAND by NAND is 1 only, I'm sorry. NOR by NAND. How many taken for OR? 3. OR and NOR relation inverter. So, 3 plus 1? 4. I repeat, how many NANDs have taken for NOR? 3. OR and NOR inversion, sorry, relation inversion, so 1 more. XOR by NAND, you remember 4 gates. XNOR, 5 gates. So these numbers I'm picking up from the previous sessions, diagrams what I have drawn, explained. And NOT by NOR, 1 only. So AND by NOR, 3. OR by NOR, 2. NAND by NOR, 4. NOR by NOR, 1. XOR by NOR, 5. XNOR by NOR, 4. Hope you'll remember all this. You don't need to by heart, which we already practiced these diagrams and you will be well remembering finally. So, I can say a few important questions here. Number of universal gates required to develop other universal gates. Number of universal gates required to develop other universal gate. NAND by NOR, NOR by NAND. See the figure? 4. NAND by NOR, 4. NOR by NAND, 4. So, number of universal gates required to develop other universal gate, 4. One more, the most important thing here is exclusive OR by NAND. So, exclusive OR by NAND. The standard answer is 4. Please remember this. And by this, we had a detailed analysis of logic gates concept, basics and fundamentals. You can say about from the beginning. Basics for logic gates and NOT, NAND, NOR, XOR, XNOR, high output with low output with input output relations, mathematical relations, math equations I can remember. And then immediate after we went with the truth table of logic gates developed, and then enable and disable inputs of logic gates developed. And then we have immediately explained about basic and universal gates. Out of universal gates, NAND and NOR, why did they been called as universal gates? And how are they developing the other gates? And which universal gate is better in what way? And all this we discussed in logic gates. Quite enough fundamental base to you to solve the questions. And I hope yesterday was the first class. You all remember well. So you solved it, the CRQ questions given back of it. You always please make sure to solve CRQ questions. Don't skip them, they will be useful as a practice for you to understand whether you are reaching the subject or not, whether you are learning all the topics or not, whether you are synchronizing with the teacher or not. Later after, what is your reachability and how many questions you'll be able to solve in CRQ. All this will help you to get the best of your gate result. If 50% role plays in listening the class, other 50% role will play, in practicing the questions. Just don't keep practicing and postponing. And this is how basic weakness of majority of students, where they will miss practicing the questions, writing the examinations, and after examinations, taking the key and getting the solutions explained. All these are very important base for competitive examinations, which I have already explained in a preparation strategy video. But please remember to do that on a daily basis. And the very immediate class, let us go with the Boolean algebra and the basic fundamental computer mathematics with a detailed analysis followed by K-maps. Thank you.